with this, again, with the sampling distribution, we've been talking for a while, we've been talking about, I'm not sure what's going on there. You got your normal curve, looks like that. With these sampling distributions of the sample means, the curve's going to look more like that. It's going to be more straight up down because you're taking what the mean is and just compacting it together. All right? Now some of our curves may not be normal like this anymore. So some of the curves may be, they may look like that or something, but we can still use all of the means. If we take a sample of a bunch of the means, and we're still going to get that normal look if we graph all those means. So the whole gist of most of it is we're taking something that maybe isn't normal and trying to change it to something that's normal. Sort of like the z-scores, when we took the z-scores and we changed the raw scores into z-scores so we could compare them all. Now we're taking something that's not a normal curve and trying to change it into a normal curve by using all of those x-bars, all those different x-bars that we found last time, because all those x-bars, what we figured out is the more and more we do, the closer and closer it's going to get to, I think ours was 2.5 last time, and it's going to keep trying to get closer and closer to that. So even if we have a curve like this, it's still got a mean, and if we take samples, those means are always going to try to get closer and closer to that original mean. So we might not be able to just draw from the entire population and get a good reading of what's going on. But if we draw little samples and then graph all those, we can get a better reading. You gotta hit pen. Oh, I hit highlighter, didn't I? Properties of sampling distributions of sample means. Again, for all this that we do, and for quite a bit of your homework, they're going to ask you to find the mean of the sample. That's not at all what I'm going to do. They're going to ask you to find the mean of the sample. Well, the mean of the sample means, which is mu x bar, little subscript x bar here, is always going to be the same as the mean of the original. So there's really nothing to do there. So if I tell you that we're dealing with that last one that we did, the mean was 2.5 when we did that little thing, drawing the numbers out last time. Well then, the mu of the sample means, of all those sample means that we got, is also going to be 2.5. No math to do there, they're just always going to be the same. The mean of the original population is going to be the same as the mean of the sample means. Standard deviation. To find the standard deviation, you're going to use this formula. Make sure if you didn't write that down last time, you got it down. So when we're trying to find the standard deviation of those sample means, of all our sample means that we're putting together, you just take the original standard deviation and divide it by the square root of n, and n stands for the number of items you're taking in each sample. Number in each sample. Last time I think we picked 2 at a time, right? So our n there would be 2. This is called the standard error. It's the standard error of the mean. So instead of standard deviation, they changed the name a little bit, and they're saying it's the standard error. Still sort of means the same thing. It's how far off you are from the mean. Population, we did this. This is what we did. All you're going to do to do all this, if I got those 4 numbers, and I want to find, first of all, I want to find all the different samples. if we're taking them 2 slips at a time like we were, let's see, random second, and this one says with replacement. We did it last time without replacement. So if I'm replacing the number each time I put it in, I could get 1, 1, then I could get 1, 3, then I could get 1, 5, then I could get 1, 7. And some of the homework problems are going to ask you to list all this. I want you to be able to find that list because I'm going to ask you to do that stuff on the test. But on the homework, because I know one of them's got like 70 different possibilities, I don't want you to list all that. That's too much work. All right? But be able to do it if I ask you to do it on the test. So we got 1, 1, 1, 3, 1, 5, 1, 7. Then you could have 3, 3. Then you could have 3, 5. Then you could have 3, 7. You could miss 3, 1. So on and so on. You got all those. And we found the mean for each one of those. So we'd add these two up. 1 plus 1 is 2. Divided by 2 is 1. 1 plus 3 is 4. Divided by 2 is 2. So on, so on, so on. But this is your sample, etc. Because I didn't write them all out. There's a whole bunch of them. All you really got to do if we're doing this and we're finding the population, we're dealing with the population and we want the mean, we're just going to take those 4 numbers, add them up, and divide by 4. That's what we've been doing all year long. 1 plus 3 is 4, plus 5 is 9, plus 7 is 16. 16 divided by 4 is 4. So the mu, or the mean of the population, is 4. The standard deviation of the population, what we're going to do to find the standard deviation is use your calculator. On your calculator, you're going to put that list 1, 3, 5, and 7 in the list, 1 in your list on your stats, and then just do the one variables thing that we've been doing for a lot of the years, and that's going to calculate your standard deviation. If I did it on my calculator here real quick, remember you just hit you just hit stat, edit. I'm going to go in there and I'm going to put in 1, 3, 5, 7. Then I go stat, calculate, one variable stats, and then you got to hit second, list 1, or whichever list you put it in, and it tells me that the standard deviation, remember we're finding the standard deviation, they give us this, they give us that as one of our standard deviations, they give us that as the other standard deviation. Well, we're doing the standard deviation of the population, so we want the sigma x, which in this case is 2.24. From that, now if we wanted to do the sample means, so all those samples, and we want to find the mean, we take mu, it's actually not mu, let's get rid of that, it's mu x bar. We take that, and it's going to be exactly the same as this, so it's just 4. It's that simple. We want to find the standard deviation. We take this standard deviation, 2.24, and we divide it by the square root of n, which is the square root of how many slips of paper we were taking at a time, which is 2. So we got this, it's 2.24 divided by square root of 2, close the parenthesis, and I get 1.58. Now if I do this, I'm just going to write this down over here. For the population, we got mu is 4, and we got the standard deviation is 2.24. For the samples, we got mu is 4, that's x bar there, and this down here should be x bar also, sigma x bar, keep forgetting that. Sigma x bar is 1.58. Let's even make this a little simpler. I'm going to make this 1.6, and I'm going to make that 2.2 so that I can show you what's going to happen on these graphs. what it's doing, if our original graph would look something like this. We put our mu, which is 4 right there, and then we go out 2.2. So up here would be 6.2, that'd be one standard deviation. Here would be 8.4, and here would be 10.6. Going down, our 3 standard deviations, that'd be 1.8. That would be negative 0.4. And then the next one, the 3rd standard deviation, would be negative 2.2, would be 2.6. So what's going to happen here is our normal curve, that's horrible, that 4 should be right in the middle, should look something like that. Now if we go with the other one, with the graph of the sample means, we're going to put 4 here, and if we sort of try to stay along these same numbers, what's going to happen? 1.6, instead of being way out here this time, we're going to be back in here a little farther. So that'd be like 5.6. Then we're going to be at 6.8, which would be somewhere about in there. Well, not 6.8. It's actually 7.2, isn't it? And then 8.8, which would be a little farther out, but that's close enough. Then we got our other 3 down here. What's going to happen with your normal curve is it sort of compresses it in. We're not out near this far anymore, and we're not out near this far anymore when you start dealing with those sample means. It's compressing it all in towards that mean.
So could you do it either way?
Well, what they're asking you to do is be able to do this, because in real life, we're probably not going to be able to do populations all the time. All right? So if we go back to like last time we talked about the tire company. And let's say you go over to Walmart in Richmond, they got a tire place over there, right? The car place. You go over there and they sell, this year they sell 600 sets of tires. Well, at the end of the year, after they sell all those tires, if we're trying to say, okay, is Walmart ripping people off by lying to them, saying that their tires last longer than they actually do, we can't go out and find all 600 people and test all their tires. So what we're going to do is go out and try to find like 4 or 5 people, test theirs, find 4 or 5 more, test theirs, and take all those samples and try to build something like this to see if their tires are actually lasting about that mean like they should. A lot of stuff, probably stuff like taxes. You guys are about that age now where you have to start doing your taxes, or your folks do them for you. Your taxes. You ever wonder why some people get audited and some people don't? Because they do stuff like this. And if your tax report, when they shove it through the computer, your tax report, you fall down here somewhere, that sets off a signal to them that, hey, that's an unusual score, or that's an unusual place for somebody to be. Most people should be in this area, and if it's unusual, then they audit them. So it'd be something sort of like this. Now again, they're not going to go through and graph out every single thing for the whole population. They're going to pull little clumps.
So the next test that we take is going to be all over this?
Well, and the other stuff that we've been doing, as far as, we've done all this stuff, finding all that earlier this chapter. Be able to graph whether you're doing, and again, this isn't a histogram, I don't know why they call it a histogram. Be able to graph it as a histogram. These are all the lists, the whole list that I didn't make, the whole thing. So that would be all the list. Then this would be the means of all of those, 1, 2, 3, 4, so on, so on, so on, all the different means. We construct the probability distribution, probability of that. Remember when we did probability distribution charts, you got all your x's here, how often they occurred, then you figured out your probability by finding the total here, how many total there are. You take 1 divided by that, that gives you that number. Take 2 divided by that, gives you that number. 3 divided by that, gives you that number. Tells you all the probability. What should all those probabilities total up to be? Should total up to be 1. Find the mean, variance, standard deviation. This is mostly what you're going to be doing on the homework. Finding the mean, variance, and standard deviation. The mean, which was 4 for the population, is going to be the same for the sample means. The variance, I'm not so much concerned about the variance. You can find the variance by using the formula. The easiest way to find the variance is to find the standard deviation and then square it, and that gives you back the variance. That way you can use the calculator all the time. Be able to graph it as a histogram. Our histogram should look like this. Again, it should be that normal curve. Should be symmetric. Central limit theorem. I think we sort of got to this last time. With this central limit theorem, all it's saying is if you have a sample size of 30 and you're drawing out all these different samples, every single time that you go to graph all those samples together, it will form a normal curve. So even though the original doesn't look normal, if we take all the sample means and put them in a graph, it will look normal. It will come out as a normal curve. Probably won't look like this. It'll probably look more like that, where it's more straight up and down. It's steeper. It's always going to be that way if your sample size is larger than 30. Now with our sample size, what was our sample size last time? How many slips were we drawing out? 2. So it wouldn't have fit this, right? But the thing it did fit is ours was going to be normally distributed anyway, because you weren't going to draw out 1 more times than 2, 3, or 4, because there was all the same amount in each one. Now if we'd stuck like 6 1s in the bag and a 2, a 3, and a 4, then it wouldn't have been normally distributed. So that's one thing. If your sample size is larger than 30, then it works for any kind of setup. The second thing is, if the population, if the original was normally distributed, then your samples are going to be normally distributed. We get all this last time. So the 2 things that you got to check for: n greater than or equal to 30. If n's greater than or equal to 30, then it's going to be normal. Your sample means are going to form a normal distribution. If the original, if the population is normal, then your sample means is going to be normal for any size n. Doesn't matter how many n's it is, how many you're taking at a time. In either case, the sampling distribution of the sample means will always be equal to the population mean. So the means will always be equal. The variance is always going to be 1 divided by n. You might want to write that down. So this is the case. The variance, which is that, squared, is always just going to be 1 divided by n. And then your sigma x bar is always going to be your sigma from the population divided by the square root of n. Those are the 3 formulas that you'll need to find This isn't really a formula to find the mean because they're just the same. The mean, variance, and standard deviation. Should have had it right there. Didn't have to do all this. So even if the population looks like this, we graph the population and it's got this crazy look to it, and that's not normal. Even if that's the case, if we start just picking 3 or 4 or 5 or 30 or 40 or 50, however many, out of this, find the mean of that, pick another sample, 30, 40, or 50, find the mean of that, and we start putting them all in a graph, they're all going to end up having that normal curve. When we put them all together, it's going to end up looking like that normal curve, even if the original looks all crazy. Cellular phone bills for residents of a city have a mean of $63 and a standard deviation of $11. Random samples of 100 cellular phone bills are drawn from this population, and the mean of the sample is determined. Find the mean of and the standard error, and I keep calling it standard deviation. You'll have to catch me on that. Remember, when we're doing it for the sample means it's called standard error, not standard deviation. Of the mean of the sampling distribution, then sketch the graph of the sampling distribution of the sample means. So we need to know, let's see, the numbers we need out of this. We know that the mean is $63, the standard deviation of the population is $11, and we're taking 100 at a time. Well, if the mean of the original is 63, the mean of our samples is always going to be 63. So to find the mean, it's just the same. To find the standard deviation or the standard error, start to do it again. Standard error, we just take sigma x bar. We take the standard deviation of the population, which was 11. We divide it by the square root of n, which is 100. That's how many we're taking at a time, and we get 1.1. And what that is doing, if your standard deviation of the original population was 11, well, that means your graph's going to be sort of real spread out. Now all of a sudden we change that standard error into 1.1. That smashes the graph in. So instead of the graph looking like a big hill, now it looks more like one real steep hill. And that's what this shows. So that if we graph the original on this same graph, where the mean was 63 and the standard deviation was 11, we start here at 63, we go out 11, that's 52, 41, so, and then we go out another one, which would be 30. So our original graph should have looked something like that if it was normally distributed, where the new one for the sample means, the distribution of the sample means looks more like this. So it sort of compacts everything in there together. Find the mean, standard error, mean and the sampling distribution, then sketch the graph. Just real quick to find the mean. Which way did it go? One backwards. To find the mean, mean x bar or mu x bar, it's going to be the same. So we looked at this, it says with a mean of 135, so the mean of our samples is going to be 135. And then to find the standard error, which is sigma x bar, we take the standard deviation of the population, which was 18, and we divide it by the square root of however many of them we're taking, random samples of size 4. So we take the square root of 4, square root of 4, which is 2. 2 divided by 18, so that's just going to equal, that's just going to equal 9. That's your standard error. And again, you see the standard deviation, how it's spread out here. Well, if we were to graph this on here, we know we're at 135 here, then you're going out 9, which is 100 and, if we go up this way, 144, somewhere about in there. And then go up another 9, that's 153. Another 9 be 162. That first one's probably not far enough out. Should be something about like that. So we got 3 standard deviations there. You come over here, you're gonna have 3 standard deviations here, and your graph's gonna look, oops, it's gonna look something like that. So it's still gonna have the same mean, but it's gonna be compressed in there. And what we can do with that is, if we're saying with this, it's talking about heartbeats per minute. If we get somebody, Michael comes into the doctor's office and his heartbeat is at about 104, which would be down here somewhere, would we consider that unusual? Yeah, so we might want to say, hey Michael, there's something wrong, we need to take care of it. We need to figure something out here, because he's way outside of what our curve is there. So it looks like that. It's, again, it's more compressed. And let's go back for a second. We can use this as normal because our original population was normal. So we didn't need the 30 or higher numbers in the sample that we were picking from. All right, probability in the sample and the central limit theorem. To transform x to z-score, you might want to write this down. So Jesse might want to set up now and write this down. So he's got this formula. Unless he doesn't want to do it, then that's fine. He just won't be able to do it. So if we're finding probability to transform an x to a z-score, sort of the same thing as we did before, except now you're using standard error. Take the value minus the mean, divide by the standard error. This out here is just the formula expanded out. Because standard error is sigma divided by the square root of n. This is x bar minus mu. You just take the value minus the mean divided by the standard error. So if you find the standard error, remember this is the same as standard, that's what standard error, what the symbol is. This is changing it into a z-score. Well, if we change it into a z-score, then we can do what we've been doing this whole chapter. Jesse was just asking a little while ago about what's going to be on the test. Well, a whole lot of what we've done this chapter is, if we find a z-score right here somewhere, if that's our z-score and we want the probability that it falls in that area, we can use our calculator or we can use the chart to find the probability that the z-scores, that any number we pick is going to fall in there somewhere. The graph shows the length of time people spend driving each day. You randomly select 50 drivers aged 15 to 19. What is the probability that the mean time they spend driving each day is between 24.7 and 25.5 minutes? Assume that the standard deviation is 1.5. So all we're going to do on this, we're not going to be able to do the whole population. So we're going to have to do just those means. We're going to pick a bunch of them. And this time we're selecting 50. We're going to pick 50 and see if that falls in the range and deal with that. From the central limit theorem, the size was greater than 30. So when we do all of the samples, it's going to be normal. We find the mean. Well, the mean's going to be the same as the mean of the population. So the mean's 25 minutes. Normal person from, what did it say, 15 to 19? Is that what it said? Yeah. 15 to 19, normal person drives about 25 minutes. That's the mean of the sample means. Then we find the standard error. We just take our sigma. What was sigma? I circled it on the other page. 1.5. 1.5 divided by, we're taking 50 at a time, so the square root of 50. And you end up with 0.212. When we graph that, notice again it's a real tall slope to it. And we're looking for the people who fall within this range, 24.7 to 25.5. And I think, didn't we figure out that our calculators would do this for us without changing all that into a z-score? So that might not be something I have on here. How did we do that? Did second vars, was it normal CDF? Is that what it was? Normal CDF, yep. So if you do second vars, I don't remember if I have this on here or not. Second vars, this is for on the calculator. And we want to go to normal CDF. And it asks us for the lower limit, the upper limit, the mu, and the sigma. So we're this time, our lower limit, we want 24.7. Our upper limit, we want 25.5. Our sigma this time was 25. And remember, for your standard deviation, you want the standard error, not the standard deviation, because we're doing the sample means. We figured out it was 0.212, we'll say. 0.212. And I'm hoping this is right. And it's saying that the area is about 0.9123. So what's the probability that if I pick a person at random, that I get somebody who drives between 24.7 minutes and 25.5 minutes a day? About 91% is the probability. If I'm right, we'll see. Now the way they do it, they write it out this way. We want probability 24.7, that the mu is between that. So it's in this range. We got that, we got that. And this is just a form to write it in. You'll see me write stuff in that form all the time. It just says probability that your X bar is between those two. They did all this math. We punched it in there. They actually changed it over to z-scores. Did it that way. You could change it to z-scores by using that formula if you wanted, or you could use the calculator, either way. And they got 0.990 is from here down. Well, we don't want this part here, so they're going to have to subtract that off, and hopefully that'll get us close to what we said it was. 0.9116, is that about what we said it was? Pretty close. We said 912.
Yeah.
All right, so that's pretty close. It's probably a whole lot easier using the calculators than doing all of this stuff. Remember on your calculators again. Let's see, I'm hoping I have this on here somewhere. Probably don't. I like working out everything the hard way. No, we'll make a slide for it. Nope. So let's do this. We'll make a slide for it real quick and I'll stick it in here.
upper and then lower than upper.
Okay, put in lower limit, 4, lower limit, 5, upper limit, 6 is mu, right?
Yes.
Actually, it's not mu, is it? Well. Do this so I do it right. So you put in your mu x bar. Seven, you put in your standard error. And you hit enter. Jesse, did you write this down so you know how to use your calculator? Liar.
I've got it. Look right back here.
I wonder how he got it, since I just made up this slide. He must be, what is it, clairvoyant? Where he knew I was gonna make up the slide.
Well, I learned this like back in like 3rd grade. I could probably teach you a few things on it, but I figured I'd let
Dalton,
you-
you're starting to understand why I say I ignore him all the time, right? Because when he says just completely ignorant things. So if you're on your calculator, you do all this stuff. See if we can get this to work. Yeah. Can read that. What's it say? What's the probability that we randomly select an undergraduate who is a credit card holder, has a credit card balance of less than $2,700? If we do this, so let's try to do this without seeing what the answer is here, and we'll use our calculator. See if I'm doing all this right. Notice that's supposed to be right there. Stupid PowerPoints move things sometimes. An Education Finance Corporation claims that the average credit card debts carried by undergraduates are normally distributed with a mean of 3173 and a standard deviation of 1120. So if we have that, what's the mean of our samples going to be?
3173.
It's the same, right? Don't make that harder than it is. So mean X bar is going to be 3173. Our standard our standard error of the samples, we're going to take this number, 1120, and we're going to divide it by the square root of, when we go down here, let's see, standard deviation, what is the probability that a randomly selected undergraduate has a credit? So how many are we selecting at a time? Looks like we're only selecting what? One. What's the square root of 1? 1. So that means this time, that's going to stay the same also. Now if we take all of that, we should be able to take our calculator. I'm using the old calculator this time instead of the new calculator. Doesn't either one. It's basically the same thing. The old calculator, you got to put in the commas. The new calculators ask you to just put them in there. So I hit second vars, go down to normal CDF. This time with the old calculator, it looks like this. I got to remember which way to do it. Normal CDF, it looks like this, and you're going to have to put in a number, comma, so on, so on. Let's see, what's the first thing we put in? What did it tell us first? The lower limit. So we want, let's see, has a credit card balance less than 2,700. So if we're looking at this, we got our normal curve here. We're at 2,700. We want anything less than that. So what's our lower limit going to be? Do we have a lower limit? No. So we just put in some crazy big negative number, like negative 10,000. All right, so we put in negative 10,000. Then we hit comma. Then we put in our upper limit. What's our upper limit this time? 2,700, comma. Then what do we put in after that? Low, high, mean, or the mu X bar. Is that what comes next? And then the last thing is the sigma X bar. So this time it's 3173, comma. Hope this works, otherwise I'm wasting my time. 1120, close the parenthesis, hit enter. Anybody else get 0.3364, somewhere around there?
Yeah.
So that means about 34%. So if we pick some random undergraduate, hopefully what a lot of you will be next year, some random undergraduate, credit card statement should say it's less than 2,700 about 34% of the time. See if that's what they got. So 2,700, they're probably going to change this into a z-score. We could change that into a z-score by doing 2,700 minus 3173 divided by the standard deviation. And you get the z-score is negative 0.42, and then you're just finding the area to the left over here. And they got 0.3372. Remember, this says probability X is less than 2,700, which is the same as the probability that the z-score is less than negative 0.42. Means the same thing. It's about the same as what we got. We use the calculator. Calculator usually give you a little different answer. What's going to change if we select 25 undergraduates.
That'd be closer.
Right, so we're gonna do this, 25, then we'd have to take this number, 1120, divided by, what's the square root of 25?
5.
And we get 224. What's gonna happen there, what that does to our graph, instead of our graph being looking like that, it's gonna squeeze it together a little more, and it's gonna be a little taller, more pushed together. So if we punch that in, let's see, I'll just do that real quick. Second var is normal CDF. We still got the same low limit, negative 10,000. Don't even really have to go down that low, but it's just a good number. High limit, 2,700. Our mu is still 3173, and our standard error is 224 this time, and we end up with .017. Did I do something wrong?
I guess that.
That seems really, really low, doesn't it? Because now all of a sudden we went from 34% down to about 2%. So now what happened here is when we squeezed this together, our graph was like this, and we were looking at stuff from right here. Well, when we were looking at the bigger curve, we had more area in there. Now that we're looking at the smaller curve, because we squeezed it together, there's not going to be very much in there. And when you do that, the other thing, you might want to write something about this down when I say it here in a second. What's the chances that we pick 50 people, or 25 people, sorry, 25 people at random, and their mean, the mean of all their credit card balance falls in that area right there? It's about 2%, right? Is it very likely that that's going to happen? No. It's something you might want to write down. Anything, because I know they ask you these questions on the homework, anything 5% or less, what do we say about it?
Unusual.
Is unusual. They're going to ask you, is this unusual? Well, is it going to be unusual if we pick 25 people that we're going to get the mean of all those people to be less than $2,700? Yeah, it's unusual because it's only about 2%. Got to make sure you can do that. Again, that was Joe's specialty last year when he was in here. He knew when everything was unusual. Anytime it was less than 5% for whatever reason, he remembered, hey, that's unusual. Didn't teach him anything else, but he knew that. All right, what happened here? That's not the right assignment.
Oh, why? Oh. Is there another slide?
Correct assignment is on page 274. That's not it though. last 8 or 9 problems there. They're odd. What do I want you to be able to do with that? Does anybody know anything about the odd numbers?
They're in the back,
They're in the back. So why would I give you the odd numbers?
Check her.
so we can.
So you can check, see if you're doing them right. Go back here and try to figure out if you're doing them right. If you just jump back here and cheat and write down the answers, is that gonna help you?
No, sir.
Now, it's gonna give you that little measly 10 points that I give you for a homework assignment. But when we take the test next week, are you gonna lose that 10 points pretty quick if you don't know how to do this stuff? Yeah. So use it. I mean, I would rather just give you the answers to everything so you could check to see if you're doing stuff right. Bad thing with that is, Nick, I can't trust teenagers that much. There's several of you who are very,
Trust
very
me.
untrustworthy. We won't mention any names, Jesse. So use that, see if you're doing the problems correctly or not, so that you can understand it.
Oh.
So pick me one, I'll do it. 2. 2. Probably helpful if you read these first, but number 2 is like a little simple. Number 2. In exercises 1 through 4, a population has a mean of 150 and a standard deviation of 25. Find the mean and standard deviation of the sampling distribution of the sample means with the given size, with the given sample size n. So number 2, we know for the population, the mean is 150. The standard deviation, that's a horrible sigma. Standard deviation is 25. We want to find the mean x bar, the mean for the samples, and the standard error, or the sigma x bar. What's the mean x bar going to be? That's one of your answers. Means have to be the same. Find the sigma x bar. You take the sigma, standard deviation, and you divide it by how many you're taking at a time. What they tell us n was this time for number 2. Somebody better help me, because we're up in the 300s. I don't know, we're on 200, you might be right.
What?
How many are we taking at a time? What? How many are we taking at a time? This is where it would have been helpful to have been awake during all of this stuff.
See, I'm looking at the wrong page. 100.
That's all it took, Riley, wasn't it? It's just Mr. Ebersole's being a jerk because a lot of people are not paying attention. So we take the square root of 100. Somebody help me out with the calculator. What's, well, you probably don't even need a calculator. What's the square root of 100?
10.
10. What's 25 divided by 10? 2.5. So that's your standard error.
See, the problem was that I wrote down 274, or 272, so I was looking at page 272, not 271.
That was sort of ignorant since there wasn't any problems to do on 272.
Well, it says number 2 right here.
It says example number 2 right there.
Well, I didn't read that.
How could you read the 2 and not read the example? The example's to the left.
No, it says example 6 and it has the number 2 like halfway down.
Yeah. So.
Other questions? We spent about 7 minutes on a problem that should have took all of about 30 seconds. Might want to find me a harder one to do. 20? Problem 20. I'll read the directions. Says, using the central limit theorem in exercises 17 through 22, use the central limit theorem to find the mean standard error of the mean of the indicated sampling distribution. Then sketch a graph of the sampling distribution. So you got to draw your graph on this one also. Number 20. They tell us that the mean age of employees at a large corporation is 47.2. So for the population, 47.2 is the mean age. Standard deviation is about 3.6. So the sigma is about 3.6. Both those are for the population. Random samples of size 36. So we also need this. N is going to be what this time? So we don't have to look it back up because that's what took so long last time.
That would be.
What did we just say? 36. We're taking 36 at a time. Our drawn population mean of each sample is determined. So we want to know what's the mean of the sample. What's the mean of the sample going to be? 47.2. That's one of our answers. Standard error. We're going to take this 3.6, divide by the square root of n, which is 36. Somebody with a calculator, help me out there.
6. That's the bottom.
That's 6, so you've got 3.6 divided by 6.
That would be 0.56.
0.6. So that's our 2 answers. That's our mean of the sample. That's our standard error of the sample. Then they want us to draw the graph. What's going to go right in the middle right here?
47.2.
Now, to show this a little bit, we'll put 47.2 right there in the middle. And then let's go by, let's just go over here and we'll go to like 44, 41, 38. Just going down by 3s. Then we'll go up by 3s. 50. You really don't have to do this, but 53, 56. I'm just doing it because I want to show what's going to happen here. That's our mean. We want to go out 0.6. So it'd be about 47.8, somewhere about in there. Then another 0.6 would be about 48.4, somewhere about in there. Then another 0.6 would be about 49, somewhere about in there. We're going to do the same thing on this side. So our graph is going to look, that's sort of horrible, but it's going to look something like that where it's real steep right there around that middle section. Where the normal curve, or the original, if we'd went out, the reason I used 3 was because this right here, because our normal standard deviation was about 3.5. So our normal one would have went way out a lot farther. Still had the same mean. That's horrible. Still had the same mean, but it would have came down. That's terrible. It still had the same mean, so it cut down something like that. That's terrible too.
Give up on drawing graphs. Drawing too much of them.
Burn out.
not anything real hard about all that? Think you can figure it out? Think Michael can figure it out?
That's a wrap.
She has a lot of faith in you, Mike.